Hi, guys. Our next speaker is Tomer Teller, Senior Security Researcher at Microsoft Azure Cybersecurity. Tomer Teller is a Senior Security Researcher and in charge of threat detection and security research. Prior to his work at Microsoft, Teller was the Security Innovation Research Manager and Corporate Technical Spokesman at Checkpoint. He's been an active speaker at industry conference and present his work at Black Hat RSA conference and OWASP.
Hello, everyone. Thank you for joining me after lunch. I know it was a hard night for everyone, at least in the industry. Everyone was looking at Petya ransomware. I'll talk about it shortly after that, the way we detected it, but I'll give you a hint. It's not that interesting, okay? We have all seen that, so everyone will talk about it. It's not that interesting. So I just want to give a quick comment. A guy mentioned that I'm a security researcher. I'm actually a security researcher. I'm what I call security PM, a project manager, which is a very cool combination of doing research and then putting a product management hat and pushing it into the product, so it won't end up in the drawer, which is pretty cool. So I'm coming from the on-premise world. I've been there for almost 10 years, and in the cloud, things are a little bit different from an attacker point of view. First of all, the attack surface is completely different. You will see that cloud makes it much harder for attacker to compromise it and much harder for customers to shoot them in the leg. This means that compromising a cloud environment, or more likely, the attack themselves, the modus operandi of attack, change drastically. This also means that the detection, in order to detect attackers in the cloud, change drastically, and it requires us to collect signals from very non-trivial locations. So today I would like to show you a couple of innovations and case studies that we've implemented inside the infrastructure and how we actually detect these kind of threats in a cloud scale environment. So before we begin, just a quick crash course on Azure. Is someone here familiar with Azure architecture? A little bit, so I'm going to make it very, very simplified. 1 second. Oh, much better. So on the left, you can see a very, very simple diagram of how a production domain might look like. So we have the network, private network. Every node on the network is a machine, and all these machines are connected to one root of trust, usually in the Windows world, Active Directory. In the cloud, however, things are a little bit different. Everything is a service. So instead of having virtual machines, of course you can upload and spin up your virtual machine and infrastructure as a service, but that's not what the cloud is for, right? You want cloud scale services. So everything in the cloud is services, no single root of trust. You can connect to each one of these services differently. Things are different. Sorry, just setting this microphone. It's okay. Oh, thank you. Oh. Okay, so these differences affect or helps us shift our mindset into what I like to call the cloud mindset. And it looks like something like this. So from an attacker point of view, the mindset was shifted, which means that instead of compromising a server, we are now compromising services. Instead of owning a domain, we now need to own a subscription. If you want to steal an identity in the on-premise world, you will go to get a domain admin. In the cloud world, that would be the subscription admin. Lateral movement. We've all heard about pass the hash, pass the ticket, Kerberos, and NTLM. Yesterday, the Petya ransomware leveraged a couple of lateral movement techniques built inside the ransomware to spread inside the network. In the cloud environment, completely different. Services don't have these kind of protocols. They're using tokens, they're using APIs, they're using connection strings. This kind of thing changed into what we call credential pivoting. Also, public IPs versus private IPs. Everything in the on-premise world, private. In the cloud, public. You can just connect to it. And of course, in order to measure it, on-premise, you'll use RDP, you'll use SSH. In the cloud, you'll probably use a management API with partial scripts. So this all shifting in mind space change the way attackers compromise organizations and cloud services, and how we, as a cloud provider, detect this kind of attacks. And this brings us to a very good detection area where I see a big rise in the last couple of months, which is anomaly detection. Now, anomaly detection is the area of identifying anomalous pattern inside time series data. We see a big rise in the last couple of years regarding new algorithms that try to detect anomalous traffic. There's a lot of algorithms. You can Google see a lot of data science presentations about how to detect anomalous traffic, how to detect deviations in the traffic or in a series of data. But there's a big problem with anomaly detection. First of all, most of the anomaly detection, when you look at it, some could be good, some could be bad, but in general, most of them cannot be attributed. If you look at the graph below, I don't know if you can look at it, it's a little bit bright. If you look at the graph below, which we'll get back to later, there's a small spike. It represents the port scanning activity in Azure in the last 3 months on port SMB. That's a clue. You probably remember what happened. But when an analyst looks at this graph and you ask him, hey, can you explain what caused that peak? They will probably say, I have no clue. So I'm looking at this port scanning activity, and suddenly someone is scanning the SMB port. I have no clue what it happened. We'll get back to it, but in order to make sense out of this graph, we need to contextualize it. Add some signals on top of this graph to make sense of it. And in order to do that, we leverage what we like to call signal enrichment. So in the on-premise world, it's pretty straightforward. You have an application that is running, you can enrich it with the process name, the user that executed it, the command line that executed it. In the cloud world, everything is a service. All the data is located in different services, which means that you need to cherry pick signals from all around the service, from all around the infrastructure, in order to build a narrative. Now, there are two types of signals that I like. I usually define two types of signals. One of them is direct signal, and the other one is indirect signal. Direct signal is usually a signal that is being generated by the service that is communicating with another service. Let's say, for example, you have a web service. This web service communicates with a client. If you eavesdrop on the network, you can pick up the network signals. This is what we're doing all of the time, network monitoring. However, did you know that once your service is doing something inside the infrastructure, of course, when you're in a cloud environment, your infrastructure is hosted on the cloud infrastructure, which means that there are some indirect or side channel signals that are being generated without you even being knowing about it. For example, hypervisor signals. The fact that when you're running something on your virtual machine, if you're spinning up the CPU too much, the hypervisor generates alerts. If you're running a ransomware on your machine and it's trying to encrypt your drive, doing a lot of CPU cycle, or running a DDoS client on your machine, the billing auditing suddenly is becoming, if you look at the graph of the billing, suddenly you will see a lot of anomaly changes, which means that if we hook up into those services and pick up those signals, we'll be able to describe a narrative. And when you will look in a graph, we can say, oh, this is not an anomaly. This is a ransomware that is installed on the machine. Or this is a DDoS that is happening outside in the network. And all of that without even being on the machine itself. So these new signals that we collect from the network help us enrich the current signals, or incriminate or discriminate signals. So this is the process of what we call signal enrichment. And when you're doing it in the cloud scale, when you hook up into a lot of services and when you collect a lot of signals, it allows you to shift the anomaly problem into what we call a supervised problem, a problem that we can label and predict better results. So this is what we're actually trying to achieve when we are in the cloud realm and we have access to a lot of data or big data. We want to shift from the anomaly problem into the supervised problem. And I'll walk you through a couple of interesting samples of machine learning algorithms that we have implemented inside our services to detect this kind of attacks. So the first one is SMT anomaly. We're looking at the network traffic quite often. We have a lot of analysts, we have hunters that were mentioned earlier. We're looking at the network traffic, the outgoing SMTP traffic, and we see that most of the time during Fridays, at some of our customers, suddenly there's some spikes. The first thing we want to do is learn more about why these spikes, why this anomaly happens. So I usually give a call to those customers or email them. Some of them are on my instant messenger or Slack. I just ask them, hey, I just saw some interesting anomaly in your organization. Can you explain that? I can tell you from now, 0 customers ever were able to tell me what's going on. I was showing him the graph and he said, I don't know. So I asked him, can you go back to the logs and say, and look whether you sent any newsletter, perhaps there was an automated script that synced your email with other emails, perhaps someone sent some batch emails, can you check it out? Most of the customers had no clue. So what we had to do is we had to build a narrative to say, this is not an SMT anomaly. We wanted to learn more about why this anomaly happened. So in that case, what we did was we partner with the Office 365 team, because eventually what we figure out when we research, all the emails that go through Azure has to pass through Office 365. Apparently, Office 365 has a very good malware team that investigates spam emails and mark them, label them spam or not spam. So we were able to collect those labels from the Office 365 team, train a model that will be able to help us infer whether a certain network anomaly is spam or not. And now only by looking at the network traffic, without even looking at the content, we don't even have access to the content, just by looking at the network, we're able to say, hey, this is spam. And this is what some of our customers are looking at. For example, possible outgoing spam activity. So if you're an Azure customer and suddenly you received an email with this content, know that there's algorithm under the hood that monitor all the net flow and IPFix traffic in Azure, cross-correlated with tags from Office 365, retrain a model that eventually speed that alert. And this happened quite often in Azure. Another interesting example is network anomalies that we see in Azure. All the time, if you have access to Azure networking backbone, you'll open it up, you'll see a lot of spikes. Suddenly TCP scans, you will see ACK scans, you will see things that looks like Nmap that is running under the hood. And most of the time, you have no clue what's going on. Now, do you know what happened when an Azure customer is getting compromised? Usually, there are 2 things that happen. One, the attacker install a Bitcoin miner on machine, or 2, the attacker join a botnet that is later being commanded to join a DDoS attack. And the reason for that is very simple. Most of the attackers know that once they compromise a cloud service or a cloud machine, they don't have a lot of time to operate until the fraud team, until the security team will find them out. So they're harvesting the extra horsepower to immediately attack others. So sometimes when we see this attack, we can clearly say, point on a machine and say, this is a machine that participating in DDoS. We see a high threshold, we see a volumetric attack. Pretty simple. We just mark this machine DDoS, and we throw it away. And we throw it away to the fraud team that eventually send them a strike, which close down the machine. But sometimes it's not that simple. Sometimes the DDoS traffic is blending with legitimate traffic. And in that case, we're not sure, is that DDoS or that's legitimate traffic? If we're not doing anything, the offenders keep using the machine. If we do something and we take down the machine, we might cause a false positive. So we're not sure yet. But the beautiful thing about the cloud, or having a visibility into the cloud view and looking at the cloud from a point of view of a service, is that I can compare the traffic of one machine to all the other machines in Azure. So what I can see, for example, is here's a machine that is definitely DDoS. Here's another machine that I'm not sure yet. However, I can see that both of them communicating with the same command and control, or both of them have been communicating with the same set of IPs, and suddenly I can attribute this legitimate machine into that DDoS and build these beautiful clusters that you see on the right, which is a real graph that represent the botnets inside Azure that we're able to cluster only by using this algorithm. So we pick up a lot of machines, unrelated machines that were joining to the same botnet, and only by joining their characteristics together, looking at all this anomaly in Azure, we were able to cluster them together. Of course, on the way, we're enriching those signals with threat intel feed. Why not? With other DDoS attack, there's all over the network, we have DDoS Defender boxes that generate alerts. We enrich the signal with those as well. Let's get back to the graph that we showed earlier. Does anyone know what it represents? This is an SMB port in the last 3 months. Can anyone say what is this peak? WannaCry. But you know it was WannaCry only a week after it happened, right? Only when they told you this is WannaCry, it was easy for you to say, okay, this is probably WannaCry. But if you go to an analyst in a SOC, in a security operations center, and ask him at point of time when that peak happened, can you explain what happened? He will probably, I'm not sure, I need to check. Under the hood, what is he actually doing? He's enriching. Is going back in time and enriching the timeline with more information. So if we take that timeline and we break it down into 3 interesting anomalies, we can see where the first anomaly started, when the first peak happened, and after the peak stopped. We can go back to this date and enrich it with news items that happened on the same day. So the first one would be the Eternal Blue vulnerability that was released. It was all over the news. It was generated Microsoft Bulletin. The next one was a Metasploit module, a public exploit that is ready to use by anyone. You just download and execute. And of course, like you suggested, the WannaCry attack campaign that started only after the peak, which means that we had at least 2 weeks in advance to notify all our customers, and that's what we did. We notified them, hey, we know that that someone scanned you because we saw the anomaly. We knew that they were part of that scan. And of course, notify them in advance to close the port and harden their environment against the vulnerability that was already out there. So the knowledge of having one-day vulnerability out there allowed us to predict a future campaign. And this is something that we're doing quite often when network vulnerabilities happen. In the case yesterday of Beta ransomware, we haven't seen this graph. And the reason is because the propagation method and infection method didn't use the SMB as well. It used it internally, but not externally. No attacker was scanning the internet to take advantage of this vulnerability. So what the attacker did was, in the case of Patya and yesterday, there were, in case you read in the news, the latest news was that there was a Ukrainian company that had a text application. Someone managed to hack the company, insert inside their update the ransomware, and once all those machines updated to the latest versions, the ransomware executed inside the machine and did something bad. But let's look at it from a threat detection point of view. What could we have done to detect that? So we know that in that case, Explorer was executing a process. In that case, it was easyvit.exe from a directory called meddoc. And this exe executed 2 more processes, runDLL and unicrypt. Now, look at the beautiful thing about the cloud view. What I can do is I can crowdsource validation. I can do something I like to call crowdsource validation. I can ask all the clients in the cloud, hey, this process easyvit.exe. Did anyone ever saw it spawning runDLL.exe? Obviously, a lot of them executed that file. I can collect all that information and immediately get statistical deviation and say, okay, this process never spawned a new process. This is suspicious. Suddenly, I'm getting more and more machines who are suspicious, and I can cluster them together. And now you're starting to understand the beautiful thing about having big data and comparing one machine against itself and guess all the others, which is pretty cool. So statistical deviations in big crowd is a big thing, and it works pretty good. Before we finish, it's important to note that my original presentation was supposed to be Cloud Insight. I was supposed to talk about cloud attacks. I changed it in the last moment because I thought it would make more sense to talk about threat detection, apparently after all the activities that happened this week. This is a slide from my original talk that I also presented in RSA this year, which aimed to talk about why the attacks in the cloud are different. The reason that they are different is because the attacker kill chain, we are all used to the term the traditional cyber kill chain. In the cloud, it's completely changed. For example, in order to attack a machine in Azure, you no longer need to do human or OSINT reconnaissance. Instead, you will try to figure out exactly what is the server, where is it hosted, what is this connection streams, how do I connect to it. The delivery of the attack, the exploitation, the fact that we no longer have client-side vulnerability, server-side vulnerability, the fact that the lateral movement is totally different, changed the game. The attacks, the modus operandi of attackers is completely different. And eventually, if we want to detect these attacks at a cloud scale, you need this kind of to build that narrative, to collect signals on top of the entire infrastructure, and these are some of the things you could detect. For example, volumetric attacks, botnet discovery, worm propagation. If you see a worm that is jumping between subscriptions or between tenants or being multi-tenant, you can do a lot of attack prediction, just like we saw in the WannaCry. And of course, you can leverage the fact that the crowd wisdom in order to do crowdsource validation, to ask someone, hey, have you seen something that the other haven't seen? Do you think it's suspicious? Do you think it's malicious? This is something very powerful. So to summarize, clouds and on-prem attack defense has their differences. We saw the difference between the cloud mind shift. Instead of attacking server, we're attacking services. Instead of compromising the domain, we're compromising the subscription. Service contextualization is critical to draw the narrative. Show you earlier, anomalies happen all the time. Most of them we cannot attribute them. We don't know why they happen. You can go back to the customer, ask him, work with him, collect all the logs, but sometimes that would be useless and not very scalable, because there's a lot of customers that cause these anomalies, and it's usually not that trivial to understand. Instead of running after all the anomalies, you need to build threat scenario narratives and pick up the right signals from the right location in the infrastructure in order to build it along the chain. And last but not least, the enrichment helps shifting the enrichment, and the fact that we handle big data helps shift the anomaly problem into a supervised problem, which eventually means less noise in the network, more high fidelity alerts, and better security for everyone. Thank you.